Hello, thank you for your interest in our paper. First, let me provide a brief overview. Complementing existing work in robustness testing, we introduced the first dataset for this purpose, which comes from an aesthetic use case where blind photographers wanted to learn about the content in their images. We called our dataset VizWiz-Classification. It consists of 8,900 images with metadata indicating the presence absence of 200 ImageNet object categories. Here we showcase labeled images from our dataset, ImageNet and ImageNet-C. Unlike these datasets, our images originated from real-world scenarios with authentic corruptions. Additionally, our images can have multiple labels. We analyzed the performance of 100 models on our new test dataset. Our fine-grained analysis demonstrates that these models struggle on images with quality issues. Now we will address the motivation behind our paper. While models exhibit excellent performance on the ImageNet testset, the important question arises regarding their performance in real-world applications and when confronted with distribution shifts. We begin by describing our process for creating the dataset. We use over 39,000 images with metadata from the publicly shared dataset VizWiz Captions. Our process for creating the dataset consists of two key parts: candidate image and category selection, manual data annotation. In first stage, we use automation to identify candidate images that likely contain the ImageNet categories of interest from an initial collection of over 39,000 images. Then we leverage human annotation to produce our high-quality labeled dataset. First, we detect which of the 1,000 ImageNet categories are present across all image captions. Then we select the categories that are obvious to lay audience. Next, we filter our initial images based on selected categories. For annotation, we ask workers to select observed categories in the image. We then included an additional task of indicating whether additional objects beyond those 10 categories are present in the image. If majority of workers identify additional objects in the image, we conduct a further review to determine the specific ImageNet categories that are present. We analyzed and compared our dataset to other popular ImageNet test datasets. Compared to other datasets, ours is the first originating from an authentic use case and also containing authentically corrupted images. Our dataset and ImageNet-C are only two datasets that support robustness testing with respect to image corruptions. Corruptions in ImageNet-C are generated synthetically, and distribution of corruptions labels is artificially chosen. The dataset allows for multiple labels per image, aiming to address these errors. Cluttered images from ImageNet using only a single label. In this example image from ImageNet, there is also a studio couch. If the model detects a studio couch, it would be considered an incorrect prediction. Also, categories with synonymous meanings within ImageNet, leading to model inaccuracies. For example, categories like lampshade and table lamp have similar meanings and are frequently found together in images. However, models are typically required to select only one label among them, which can lead to potential inaccuracies. We then benchmark a wide variety of models on our dataset. We selected 100 models for evaluation on our dataset. Models are divided into three subclasses. Standard models train on ImageNet and do not benefit from any methods for increasing robustness. Models trained with more data train on a larger set of training datasets such as ImageNet 21K. Robust models leverage robustness intervention methods such as data augmentation and adversarial attack methods. We compare accuracies of models with respect to different quality issues and clean images. The order of performance gap based on the image quality issues, from the lowest to highest, is dark, blurred, framing, bright, rotated, and obscure. Here we aim to evaluate the robustness of models to distribution shifts. We can see that models trained on more data can produce effective robustness. There is a large performance gap even for clean images. Now we compare the performance of models on ImageNet C and our dataset. Models with leveraged robustness intervention are over-optimized for synthetic corruptions and cannot simulate real-world quality issues. To examine to which extent the natural distribution of categories of our dataset affects the performance of models, we split our dataset into three subgroups with respect to the number of images per category for frequent, common, and rare objects. We can observe that unbalanced labels in our dataset is not an important factor for finding the robustness of models, because the performance of models follows the same trait in each group. We can see that performance gap exists in all distribution shifts. The most robust models are models pre-trained on larger datasets. Now I will summarize the findings and conclusions of our work. Our dataset is the first dataset from an aesthetic use case, specifically from people with visual impairments. Quality issues which our images can have largely affect the performance of models. The performance gap is measured between our new text dataset and ImageNet dataset. Progress on ImageNet C doesn't ensure similar progress on our dataset. The most robust models are models pre-trained on larger datasets. Please join our dataset challenge. Thank you so much for your attention.